Welcome back. In this video, you will learn how to approximate solution of a first-order initial value problem. Let us first recap what such an initial value problem looks like. An initial value problem consists of two parts: an ordinary differential equation and an initial condition. The order of the initial value problem is equal to the order of the differential equation. Here we have the general form of a first-order initial value problem. The differential equation describes the derivative of y as a function f of t and y. If f is smooth, the differential equation has infinitely many solutions. The initial condition assigns a value to y at an initial point t0. The initial point is often referred to as the initial time. This is because many initial value problems describe how the variable y changes as a function of time. A differential equation along with an initial condition has a unique solution. Or, in other words, an initial value problem has a unique solution. Pictured are some common examples of initial value problems. The population growth model describing the population of the king penguin, the mixing model describing the change of a contaminant in an open system with in and outflow. As a third example, one can also describe the height of the fluid in this tank. Given a periodic inflow and using the law of physics to determine the outflow, this results in the initial value problem on screen. These three models show the rate of change over time given a certain start value. You have seen in your calculus course that if a differential equation is solvable, then the initial value problem containing this differential equation is also solvable. The first-order differential equations that you have learned to solve analytically fall in one or both of the following types: separable differential equations, like the penguin population model, and linear differential equations, like the mixing problem. But what can you do if the differential equation does not fall into one of these two categories, like in our third example of an initial value problem? Sadly, it is not always possible to get an explicit expression for the function y of t. What you can do is approximate the value of y for a given time. Let's call this time t1. To find this approximation of y at time t1, we introduce a faux separation of variables method. Starting from the differential equation, we multiply both sides of the equation with dt and integrate. This equation looks similar to what we find when applying separation of variables. However, this is not a true separation of variables. The dependent variable y is still present in the integral on the right-hand side. And since the function y of t is unknown, there is no general way to determine the antiderivative of f in terms of t. Instead, we want to use numerical techniques to approximate this integral. As you might recall, only definite integrals can be numerically approximated. So the next step is to select a set of boundary terms for t and y. Remember, the goal is to approximate the value of y for a given point t1, and the value of y is known at point t0. So it might be a good idea to integrate over the domain t0 to t1. The boundaries of the integral on the right-hand side of the equation are clearly taken from our choice of integration domain. But what happens on the left-hand side? Since the integral is over y and not t, the boundaries need to coincide with the boundaries in t. Or in simple terms, the lower boundary is the value of y at time t0, and the upper boundary is the value of y at time t1. Now, the value of y at time t1 is exactly what we would like to approximate. And even though y is still unknown, the integral on the left-hand side can be calculated directly. This last equality can also be obtained by applying the fundamental theorem of calculus to the differential equation. How nice! The left-hand side of the equation now has one term that we want to approximate and another term that looks very familiar. Of course, it is the initial condition. This is why it's important to start from an initial value problem and not just a differential equation. We also see that the integral on the right-hand side is now a definite integral and can thus be approximated using any of the numerical integration methods you've previously seen. For example, the left rectangle rule. The final approximation of y at time t1 is the initial condition plus the numerical approximation of the integral of f from t0 to t1. Let's say you want to approximate the value of y at a second point, t2, where t0, t1, and t2 are indexed in an ascending order. Then you can repeat the process and integrate over the domain t1 to t2. You can use the approximation you found for y at time t1 as an estimate for y1. Repeating this process, the function value of y can be approximated for a given set of ordered points t1 up to tn, where each yi can be replaced by the approximated value of y at point ti. In this video, we derived the equation necessary to approximate the value of y at a point t1, given an initial value problem. We have also seen that this approach, by extension, this equation can be repeated to approximate the value of y at several different points in time. In class, you will take the next step and actually apply numerical integration methods to approximate the integrals in these equations.